Our second speaker is Ayush Srivastav, who is currently working as Assistant Manager of Systems Integration in Ola Electric. He is mainly focused on system simulation and battery performance and cell requirements. He has filed for 3 patents while at Ola and has published in notable journals and conferences around the world. He has worked with institutions like KTH Sweden, KU Leuven, AIIMS on research projects. He is recipient of Dr. APJ Abdul Kalam Young Fellowship Award in 2022 and was also selected under International Youth Exchange Program in 2021. He graduated from NIT Bhopal in 2022 with a bachelor's degree in mechanical engineering. I welcome Ayush to enlighten us about factors that affect battery range, as range anxiety poses the big challenge for EV penetration. Yeah, welcome Ayush.
Hello everyone, I'm Ayush from Ola Electric and I'll be presenting our paper today. I'll be focusing on 2 things. First, the factors which affect range, and secondly, the battery temperature. I'll be telling you exactly how we use GT Suite to achieve these 2 tasks. I'll start by going through some stock company slides. I'll give you an introduction of our paper and what methodology we use to achieve these tasks and some impacts and results. Let's start with Ola Electric. So as you all know, Ola has been the largest ride-hailing platform in India for the past 12 years. We serve across India, Australia, New Zealand, and even UK. But serving the mobility platform, the ride-hailing business, we have tried to expand it to a mobility sector. So we have launched Ola Electric. So Ola Electric was started in 2019, and now we have some very great R&D centers and a future factory. In the R&D center which I'm displaying here is the Battery Innovation Center, which we have recently started in the past year. Here we are trying to develop new cells. We'll be developing cells such as 21700, 14680, and we are also planning to develop the standard cell 18650. And in the future factory, we are manufacturing scooters. Our current manufacturing capability is around 800 scooters per day, and we are trying to expand that to even more. Yeah, so this is the current lineup of our products which we sell. Our top product is S1 Pro, which is currently being sold very well. As you can see the numbers, it has been sold over 1 lakh units. And this number I think is 1 month old, so it has probably been increased by at least 2,000 or 3,000. So this is the current lineup of products. You can see the S1 Air product, which we have launched but is not yet delivered. It will start delivering in June. And you can expect the delivery by June, which is going to be a low performance product, but it is going to serve the Indian market very well. Now coming to the slides, the paper which I'm going to present today. So as I said, the current impact in the EV industry, which is hindering the sale of EV products basically, are 2 factors. The fear of range and the fear of battery related incidents. We have seen in the news a lot of battery incidents in the current scenario and the current years. So I'll focus on how we are planning to tackle these 2 problems. So we have developed 2 models. First is the vehicle model and second is the battery thermal model. Using these 2 models, we are trying to tackle both of these factors and how we can predict this in early stages and try to find a solution for them. These are some factors which we think are affecting the range and the battery temperature in a vehicle. These are some factors based on intuition and the basic engineer's idea of how a vehicle works or how a battery pack works. So how are these factors actually affecting? What is the number which plays a factor in the vehicle? I'll be shining some light on that. And similarly for the temperature, what are these factors actually contributing in the vehicle? So coming to the methodology now. So how are we developing the vehicle model and how we are trying to better or improve the range of our vehicle? So this is the vehicle model that we have developed for our S1 Pro vehicle. As you can see, it's a pretty simple vehicle model. We just have a battery, a motor, the vehicle, and all the controls which are required to function the model as the vehicle is functioning in actual. Coming to the methodology of how we are developing the battery thermal model. So the battery thermal model is basically an FEA model. So it starts from the CAD of the battery. As you can see on the left side, this is the CAD of our battery pack. Now to model the entire battery pack in form of an FEA model, it's not wise to take the entire battery pack. So we have taken a section model of the battery pack. It is selected at the center of the battery pack so that we can have a fewer number of cells and fewer number of components. Even in the experimental data, as we have sensors in the battery pack, we do have a sensor which senses the temperature at the center of the battery pack. So we are using that particular sensor to get the data and validate it with our simulations. So this is how we have developed the battery model. As I said, it is a section model. So you can see the section of the battery pack has been taken. It has been developed as a meshed model in FEA, and that model has been transported to GTIC. And then what control logics we are using to, not control logics, basically what are we using to get an accurate match of the temperature, I'll tell you. So this is the overview of how the battery thermal model is working. So basically we have a battery template which calculates the heat dissipation from the battery based on the DCIR that is being input as in the form of a map to the battery template. That particular dissipation is taken in the battery thermal model and is being fed to each cell. Now based on the material properties of the cell increases in temperature. We are losing some heat to the environment that has been incorporated, and that temperature increase in the cell is being fed to the battery pack again. So this particular feedback loops work very well, and this is how we are getting the results out of it. I'll show you the battery results a little in some while. First, we'll focus on the vehicle results. So as I said, the factors which affect the range in a vehicle. So the factors which I mentioned in my previous slide are being studied individually here. So first, I'll focus on the vehicle weight. How is the vehicle weight impacting the range of the vehicle? So the graph which I have presented here is basically a graph in which you can see from the right to left, the vehicle weight is being reduced, and from bottom to top, the percentage improvement in energy consumption and range is being shown. So as you can see, as soon as the vehicle weight starts to increase, there is a particular percentage of energy consumption improvement decrease and range decrease. These particular values are being shared with our mechanical team so that they can accordingly design the vehicle, reduce the weight wherever they can, and how much benefit we can get by reducing this much weight. So we have some actual values in the initial stage so that it can help the designers reiterate their designs and arrive at a particular weight which is good for the vehicle. Similarly for the motor efficiency. So the motor is being designed by the motor team. But as soon as the motor is being designed, they provide us with some efficiency map. That efficiency map we use to see what range will be delivered by the vehicle and how the vehicle will perform. But in order to improve the range, motor is a very important component. So we just make a lot of simulations with different drive cycles. We share the results with them of how they can improve, at what operating point should they improve the efficiency of the motor. And through electromagnetic simulations, if they can get a better efficiency, they redesign the motor and give us an improved efficiency. We're using the different efficiency now to see how much range improvement we can get. As you can see, I have quoted a 6.2% increase in range by doing this particular activity in conjunction with the motor team. Now some other factors as well. So road loads. How is the vehicle facing resistance while on track? So as you can see, if we reduce the resistance to the vehicle from low rolling resistance to ultra low rolling resistance, we're getting an improvement in range by 7.2%. This particular DOE is done by us with different tire manufacturers of how much resistance is going to be provided to the tire, or what is the data that we are getting from GARC, or how are we performing the testing in the test facilities. According to that data, we are doing some iterations. We are getting some rolling resistance coefficients, and we are seeing how much improvement we can get in the range. Now similarly for this pedal map. So it is pretty interesting what we are doing with the pedal map is that we are trying to iterate, and basically it is an iterative process in which we are trying to define how much torque we want to deliver at particular RPMs through the motor. So as you can see, I have put 3 graphs over here. So first one is the linear, the blue one. So that is a torque pedal map where we provide a linear torque with the increase of RPM. So that is giving us a particular energy consumption and range. But if we are trying to reduce it a little, let's say the Indian customer is not in requirement of that much aggressive torque, or he prefers to drive a little slow. Based on the customer habits, we can define how much torque is required in the actual Indian market. Based on that, we define a 2D map based on the pedal position, how much pedal is being pressed, how much RPM the particular motor is delivering, and what should be the torque that should be delivered at particular torque and that pedal position. So it's an iterative process. We have to do it again and again. But if we get at a very good value of the pedal map, you can see we can get an improvement of around 3.3% range in the conservative map. So that is what we are planning to implement in our vehicles. Now coming to the results of the battery thermal model. So as soon as we have developed the FEA model of the battery thermal, we ran a simulation with our mode 3. The mode 3 is our most aggressive mode in which the vehicle performs most aggressively. So you can see the drive cycle in which the vehicle was driven for that particular data, for that particular drive cycle. We have taken the data of the temperature increase from the central temperature sensor in the battery pack. And that data is being compared to the simulation, and the experimental is also shown. So in the mode 3, which is our most aggressive mode, we are seeing a difference of around 5.5%. And this difference in results is being improved as soon as the aggressiveness of the drive cycle is being reduced. So you can see, I've presented the results of all 3 modes here. The mode 1, mode 2, mode 3. So you can see the results which I'm showing. So as you can see in mode 1, the match is pretty accurate. In mode 2 also, it's acceptable. Only in mode 3, at one particular case, where the acceleration was very high, we are seeing a difference of around 5.5%. Otherwise, the battery thermal model is working very well for us. So now, how are we using GT real drive? We have developed this model. We have a vehicle model and a battery thermal model. How are we predicting the real world conditions using these two models? And how are we planning to reduce the testing in our vehicles? So we are using GT real drive to get this particular task done. So as you can see, I've shown two results here, one from Manali and one from Bikaner. So Manali is the low ambient condition and Bikaner is the hot ambient condition. So I've shown the results of two cases over here, and we are taking the road condition, basically the map, how is the distance being traveled, what are the directions the vehicle is taking, and what is the elevation of that particular location from GT real drive. We are running it through in our vehicle model and the battery thermal model, and we are seeing what results we are getting. So this is how we are getting the results in a cold ambient condition and a hot ambient condition. So you can see the drive cycle which we are getting from GT real drive, and what is the corresponding temperature increase in that particular drive cycle for that particular vehicle using our vehicle model and our battery thermal model. So my presentation was short. I'll come to the conclusion. So using these two models, what have we achieved as a company? So we have achieved how to improve the range in our particular vehicle. I have presented 4 factors over here. So we are focusing on many more factors, but for the brevity, I have presented only 4 factors here. So we are trying to reduce the vehicle weight, to improve the motor efficiency, reduce the rolling resistance, and propose a pedal map which is best for the Indian customer and gives us the best range. And using the battery thermal model, we are trying to predict how much maximum torque we can allow to the motor. Based on that, we get a current value. And based on that current, how much temperature increase we'll get in the particular cell of the battery pack. And is that acceptable as per us or the cell supplier? This is what we are trying to focus on. Similarly, we are trying to see is there a requirement of forced cooling in the battery pack? Is the temperature that high that we need to install some cooling mechanism near the cells? As this is the two-wheeler, we have low number of cells. There is no current requirement for a forced cooling, but this can be predicted using the battery thermal model. And similarly, we can define some deration strategy in the BMS. We come to know what is the maximum temperature increase at the extreme locations in India. And based on that, we can define a deration strategy in the BMS that we don't want the temperature to go higher than this. Coming to the impact of my project, what we have achieved here is so to get all this data of range improvement, energy consumption, whatever we do, we used to do testing in GARC. So in GARC, we used to do range, acceleration, regeneration, energy consumption, and gradability testing. Using this model, we have reduced that testing, and we are able to achieve the same results using our models. And similarly, for the battery thermal model, we used to do some testing at extreme locations such as Rohtang Pass, Leh, and Jaisalmer. We have reduced those testings by using this battery thermal model, and we are able to get accurate enough results that we can trust them and move forward. In conclusion, I would like to say that we are using GT very well, and GT is able to help us reduce the cost by 1/10 the amount that we spent on testing for achieving the same results. Thank you. I'll take any questions if you have.